Hello, and welcome to Section 2.7, Derivatives and Rates of Change. You need to remember Section 2.1 as we talk about this section. We're going to be revisiting that concept of the slope of a secant approaching the slope of the tangent to a point when you move another point closer and closer to the point you're interested in. So this section is kind of putting everything together that we discussed up till now. You remember how talking about this point approaching P was the concept of a limit, but the slope of the secant is approaching the slope of the tangent. Then we later went on to talk about actual limits of functions where an x value is approaching some other value. What is the y value of the function doing when that happens? So that's where we discovered limit notation. And so we should be familiar with that limit notation. So this is just telling us that instead of plugging in, so many different values for q, I'm letting q be represented by x, f of x, and those values of x are getting closer and closer to the value of a I'm interested in. In this case, a is 1 when you're looking at this graph. So let's look at an example of how to use this. So I have the function f of x equals x cubed, and I want to find the equation of the tangent line at the point 1, 1. So using limit notation, I know that I can find the slope of the tangent by taking the limit of the slope of the secants as they approach this point 1, 1. So generalizing that slope formula with the limit, f of x in this case is x cubed, f of a in this case is 1, so f of a is 1 cubed over x minus 1. And then now we know how to evaluate this limit now that we've been through sections 2.2 and 2.3. So this limit is 3. So the slope of the tangent at this point for the function f of x equals x cubed is 3. So now if we want to get the equation of the tangent line, we know that the slope is 3, the point 1, 1 is on the line, so we just use the old slope point form of a line, and that's our equation. Here's another example, but this time with the function f of x equals 4x minus 3x squared at another point. So I do the same thing. My a is 2, so there's my function, right? My a is 2, and f of x is 4x minus 3x squared, and that evaluates to minus 8. And again, my equation of the line, there's my slope of minus 8, there's my y value, and my x value of my point 2 minus 4. Another thing we re-examined in this section that we touched on in section 2.1 is straight line motion. So we have a position function which is given by f of t, and the position function is giving us the position of an object from the origin at some time t. So this is used a lot because position per unit time is velocity. It's a rate. What's the change in position per unit time? So you'll see graphs like this. It's a straight line graph. So time is not graphed here. So this is just showing the position of an object at a time relative. So it's showing the position, the displacement from the origin. So for example, this blue point is the point when the object was 5 meters from the origin, and that occurred at time t equals a. The object has moved 14 meters from the origin now, and that has occurred in h seconds from that time t equals a. That's why it's f of a plus h. So we're looking at relative changes in position and the rate at which that occurs over some time interval h. So remember, the average velocity is the change in the position divided by the time interval. And we know that we can take the limit as h approaches 0 that means that that time interval is getting smaller and smaller, and our velocities are approaching the instantaneous velocity when h is 0. And it's the same type of concept as letting q approach p. Same concept. But instead of intervals on the x-axis shrinking, units of time here are shrinking, h. So if we take this straight line graph and we turn it on its side, so here's where the position of the object was, and now we graph it versus time. This is a normal XY graph now that we're kind of used to, and this is the graph of that position function. So this shows it starting at the origin, it's going away from the origin, and it's reached whatever this distance is from the origin, must have turned around and traveled back to the origin, and then turned around again and is traveling away from the origin. So notice that even when we graph it like this, at time A, as we let another point approach time A and let those intervals get smaller and smaller, we have that same formula, f of a plus h minus f of a over h.